going to basically just be explaining the difference between an event that is and is not mutually exclusive. So yeah. All right. So what is the difference between events that are and are not mutually exclusive? What I've come up with is that two events are mutually exclusive if they cannot occur at the same time. In another word, that means that mutually exclusive is disjoint, which means there's just two circles separate, and such as on a Venn diagram, they're not intersecting. If two events are disjointed, then the probability of them both occurring at the same time is 0. So here you can tell if it is mutually exclusive on a Venn diagram. The non-mutually exclusive ones are, in fact, jointed, which means they're just intersecting. So on the right picture here, you can see that there's that little purple section. That just shows that that is a non-mutually exclusive event. And then how would I rephrase the meaning of an event would be when occurrence or outcome of many possibilities given from an experiment, which just means you're going to have multiple possibilities. You're not going to have just one. And that's all I have for you. All right. So, Andy, can you get yours up there? Do I have to hit stop share?
Yep, I'm good.
All right.
Hello, my name is Andy Spurl, and I will be sharing today the additions to calculate probabilities, as shown on the formula in front of me. Addition to calculate probabilities. Probabilities were actually created by a gentleman named Reverend Thomas Bay. Now, Bay's solution to a problem of inverse probability was presented in an essay towards solving a problem in the doctrine of chances, which was read to the Royal Society in 1763 after Bay's death. Richard Price Shepherd, in his work through this presentation and his publication in the Philosophical Transactions of the Royal Society of London the following year, this was an argument for using a uniform prior distribution for a binomial parameter and not merely a general postulate. This essay contains a statement of special case of Bayes' theorem. In the first decade of the 18th century, many problems concerning the probability of certain events given specified conditions were solved. For example, what is the probability of drawing a black ball, or the converse given the one or more balls have been drawn? What can be said about the number of white and black balls in the urn? These are sometimes called inverse probability problems. Okay, so in front of this slide I have here, it's asking for addition probability problems. And I have a problem here in front of you. And what it is asking is to find the probability of a mutually exclusive event following these steps. First outcome of the problem, we're going to find the total of possible outcomes for the problem. Then we're going to find the desired outcomes, and then create a ratio for each event. And then after that, we are going to add the ratios or fractions of each event. So first what we're going to do is we're going to add the total possible outcomes of a six-sided die, which are 6. You have 6 different possible outcomes when rolling the die. Second, you find the desired outcomes. Person here, Cheyenne, needs to roll a 3 or 6. Therefore, a 3 or 6 would be desired outcome. A 3 appears on a six-sided die once, and so does a 6. Remember this information for your next step. Now, third, what you're going to do is create a ratio for each event. This event, rolling a 3, would be a ratio of 1/6, because the die only has one side with 3 dots. The second event, rolling a 6, would also be a ratio of 1/6, because the die only has one side with 6 dots. Now, what I'm going to do here, come on. is we're going to add the fourth ratio or fractions of each event. And this step will give you the probability of rolling a die and getting a 3 or a 6, which is 1 over 6 plus 1 over 6, which would equal 2 over 6. And then you can also take that lower to 1/3. Therefore, Cheyenne has a 1 in 3 chance of rolling a 3 or a 6 when she rolls a 3 or 6. Now here I show a table below. This table below shows the 6 possibilities for a die, 1 along the left column and 6 possibilities for die 2 along the top column. The body of the table shows the sum of the die 1 and die 2. The colors of the body of the table to the right illustrates the number of ways to throw each total. The probability of throwing any given total is the number of ways to throw that total divided by the total number of combinations, which the total number of combinations is number 36. In the following table, the specific number of ways to throw each total and the probability of throwing that total is shown. So up here above this diagram here are the number of combinations, first with the total, the number of combinations following that total, and then the probability for each number of those combinations. And to the right is a diagram showing which part of the total, the number of combinations, and also what the probability of those combinations are for the answer for the question. Now I'm going to show you some examples of the real-life probabilities that we use in our everyday lives. And please note these are used in everyday lives, and we're actually not really aware that we're using probabilities when we do this. Nearly every day you use a probability to plan around the weather. Now, meteorologists can predict exactly what the weather will be, so they use these tools and instruments to determine the likelihood that it will rain, snow, or hail, for example. If there's a 60% chance of rain, then the weather conditions are such that 60 out of 100 days with similar conditions it has rained. Now, you may decide to wear boots rather than shoes, or take an umbrella with you to work. That is one probability that you use every day. Now, the next probability, you use probabilities all the time when you play board games, card games, or even video games that involve luck or chance. You must weigh the odds of getting the cards you need in a poker game. Or say you're playing a video game and you want to get that secret weapon you need in a video game or defeat another player in a game as well. You also use probabilities for all 3 of those things in your life. And finally, calculating the probability of a single random event. Now what you're doing here is you're defining your events, and the outcome probability is the likelihood of 1 or more events happening divided by the number of possible outcomes. Divide the number of events by the number of possible outcomes, such as here, choosing a day that falls on the weekend is our event, and the number of outcomes is the total number of days in a week. Now you have 7, which is the number of events, is 2, since the 2 days out of the week are weekends. And the number of outcomes are the following in this equation here. So the number of outcomes we have is 7, which has a probability, so we're going to be taking 2 divided by 7, which equals 2 over 7, or 0.285, which also gives us a percentage of 28.5% on this equation problem. And that's how you addition to calculate probabilities. Have a wonderful day.